I saw it. No, I didn't get this.
All right, guys. All right. Let's get the lecture started. So today we're going to mainly talk about the remaining part of the serial bus. The last lecture we talked about like the overview and then the UART protocol. In today's lecture, we're going to mainly talk about the SPI and the I2C protocols. Before we jump into the class materials, some announcement. The midterm 1 grade request is going to be ending tonight. So if you still think of some, mistakes are made while we grading your exams, or some partial credits should be given for any of your answers, please make sure to submit the request by tonight. And then second thing is the team registration is also going to be due tonight. Last Friday, we had our very active team formation event, and we have posted a Google spreadsheet online on the Piazza, as well as on the class website. So if you were to make sure you register on the slides, I can show you where that is. So basically, if you go to the assignment, and there's the spreadsheet here. Make sure you have your team assigned on the same column, and if you are in like a 5-people team, put your name on the notes, indicating you are the 5th member. We're trying to enforce all the groups to have like 4 people, give around 4 people, but we ended up with like I think two groups or so with 5 people, which hopefully should be okay. But you guys still have to work on more complicated designs for the final project in order to have like the same degree or like same amount of complexity while considering against other 4-people group in general. Any questions on the team formation? Anyone who still doesn't have a team at the moment? Okay, perfect. Cool, so the homework 5 is going to be due this Friday, and then after this we have basically 2 more homework, and then we're done for all the homeworks. And you guys will have the spring break, and then come back that we're going to have like a quick midterm 2, and then it's all for final project. So that's where all the real fun going to begin. Cool. Any questions regarding any of these items, midterms, team registration, or homework 5? All right, nice. So yeah, a little bit on the lecture outline today. Basically, we talked about the serial bus architecture overview last lecture, as well as the UART, the Universal Asynchronized Receiver and Transmitter Protocol. Today, we're going to talk about SPI and I2C. We're going to start with the SPI, the Serial Peripheral Interface. Just like before, in case you have additional time and want to dig into this concept in more detail, we have the sections in the STM reference menu that you can look at. Also, we have one of the recommended textbooks that have one of the chapters, like we said last time, dedicated to the serial communication protocols. So there is also a section inside that's talking about SPIs, in case you want to learn more nitty-bitty of how this protocol works in a more hardware level. But basically, SPI is a serial peripheral interface. It's like a high-speed synchronized as opposed to the previous UART, asynchronized. This one's a synchronized. And it's fully duplex serial communication protocol, meaning it can do data transmission in both directions, and fully, meaning it can do it simultaneously. Basically, it's usually used for like chip-to-chip communications, and normally, if you exclude the ground pins, etc., ground or power pins, usually it uses 4 wires for the communication. We'll go into like more details of each of these wiring in next slides, but basically these protocol allow you to have like pretty high speed transmission data rate, and it does not have like a super fixed data frame as opposed to the previous UART. This one, it can be a bit length communication of 8-bit, 16-bit, 4-bit, kind of up to you to like decide, basically. Oh yeah, one of the more important things, which basically this SPI only allows one master to talk to a bunch of different slaves. That's one of the main distinctions you will learn later when we talk about I2C. But basically, these are the wires, the 4 wires that's going to be used. They have different names. So you will see on chips nowadays, it either says SDO or SDI, meaning on this chip, from this chip's perspective, it's serial data out or serial data in. Sometimes you also see like, MOSI or MOSI or like MISO. Basically, those are from like the master's perspective. That means this wire is for the master out slave in. And you can tell by the name, basically, that means it's the data line that used from master to send data to slave. And then MISO is the other way around. It's the input, it's the output from the slave devices to the master device. And we also have the S clock, basically the system clock that's being shared across the entire, like, however amount of peripherals and controllers or masters connected inside of this one SPI communication. And that system clock is what's used to synchronize all of them together. And how do we know which, like, among these data lines, which data is being sent to whom or at what time? Basically, we have this additional select pin, CS. It's called, not computer science, it's called chip select pins. That's basically one per peripherals that's going to be, selected based on whether it's currently talking to this peripherals or not. It's usually being put to low one day, yeah. And the controller or the masters will be the one who generates the clock. Usually it's basically just the system clock that's being shared across these peripherals. And how do they do the data transmission between each other? They basically have the shift registers that in one of any of the data in and out pings, basically one bit goes in and one bit goes out. That's how it's able to do like the fully duplex communication. So one bit comes out of the master out, and then the corresponding slave will basically push one bit back in. So it's kind of like a rotating communication mechanism. So that's basically how they achieve the synchronized and simultaneous data transmission between the master device and slave devices. Any questions on this wiring here? It's very important to remember, basically, the SPI only allows one controller or one master in each of these communication protocols. Okay. So yeah, this is a little bit in more details on the data exchange that's happening between the master and slave devices. Basically, you remember, like, from previous APB buses, we have the lines that will be raised or lowered if the data is being received. Like we have, say, the P write or the P write pins that goes to all peripherals, and a dedicated P ready that comes from the peripherals to the controllers, indicating if it's done with its operations. This is not happening inside of the SPI. Basically, all it does is just doing like this shifting thing between these two shift registers. One bit out to the peripherals and one bit back into the SDI line. So basically, this little shifting mechanism. And yeah, so they are, additional to that, there is like no flow controls or acknowledgement bits. Acknowledgement bits, later on we will talk a little bit more about this, is some like one bit that's used in I2C that's kind of tells you whether it's, if it's received the request, and also whether it's done with the request, so to speak. And in the SPI, there's no such acknowledgement things. So in addition, the peripherals cannot communicate with the controllers directly. So typically, you will not be able to say like, "Hey, I want to swap between the shift registers from the slave." It's always the masters who send out this data exchange command, basically. So how does any of these peripherals actually get the attentions of the masters, right? There are various ways to do that. I think most common ways you can do is you have the slave devices connected to like additional GPIO pins, etc., and kind of like take advantage of the interrupt hardwire of that GPIO pins. So whenever something immediate needs to be happen or like being detected by that peripherals, it kind of tells the or changes the stats of that GPIO pin, and that GPIO's pins embedded interrupts going to be triggering the controller or like triggering the main program, and then that going to cause the controller and do something to see if there is any immediate attention needed. There's also some other techniques for like polling or like daisy chaining. It's a little bit less, well, it's still being used. So basically what they would do is they kind of, like the peripherals, like the slave, they just keep pushing whatever the data it has to the next SPI protocol, and eventually it will fulfilling the whole cycle and go back to the master. So imagine like master is constantly checking on at least like one of the peripherals, and at some point that data gets to it. It's not as efficient, but it requires less wiring. So different method. I think for your final project, you probably will use like the interrupt signals ones. I think that's more straightforward and easier to implement. Okay. Any questions on how they do the data communication and data exchange here? All right. Let's next do like a quick example of how, so this is only on the data sending side. So essentially, SDO from the perspective of the master device, we don't show how the data go back to the master. But yeah, let's look at it together. Okay, let's see if it works. Basically, if I reset, and you will see that, oh, okay. Let me first turn this off. So this is basically a load signal that tells the SPI master to send out the data. And these two are the select pins. For example, I want to select the, actually, if I put both of them low, so none of the data is getting through, even if I turn up the load register here. Okay, can you guys see it? Okay. Yeah, so basically none of the data is going through. And say after this 8 clock cycle, I change maybe the top one to high. And then next, we should be able to see, should we? Okay. Okay, here we go. Next, we should be able to see the data got transmitted too. So basically, we have like one additional control pins that's like the chip select pins that's being selected to deal with or like to selecting which of the peripherals will be receiving data. And they have a shared SDO and SDI buses. Yes?
Where's that select pin?
It's very small. Okay, so this is the select pin 1, and this is the select pin 2. And you can play around with it by changing it to high and low, basically. Yeah.
And which line is which on the bottom?
Which line is with what?
Sorry, which graph? Which graph on the bottom is like which line?
So this line is the data line that's transmitting, that's being shared by both of the, peripheral devices. This is the device 1, and this is.
Which waveform is which on the bottom of the 4?
Oh, I see. Okay. Let me. It's been cut off. Sorry. Yeah. So on the bottom, the second line is basically the clock, system clock, and here, this is the system clock, and this is the serial data out from the perspective of the master device. And then these two are the two chip select pins for two of the device. Yeah.
Which part of the SPI drives this chip select pins? Would it be the controller, or like what would drive the chip select pins?
Yes, so typically it would be the controller or the main program that would be the ones who decide the chip select pins. Yeah, the slave device or the peripheral devices here cannot turn the select pin on by itself. Cool? Yes?
In SPI, when you talked about how the data out and the data in, it just shifts the bits over and sends them?
Yeah.
Can you explain that more?
Yes, so for this one particularly, it's we're only showing the data sending part from the perspective of the master. Imagine you have that register, shift register, also connected back to the master protocol. Whenever it pushes a data in, it shifts the data in to the shift register. It shifts the data out. That could potentially go back to the master device. Yeah, sorry we didn't draw that in the circuit, but that's basically how it works. So basically, in each clock cycle, it's able to do that two. You can think of them as like two operations, although it's done within like one clock cycle.
So each peripheral and like the master and the peripheral has two registers that get the data in and the data out, and they're each connected to their own shift register.
Yes. Any other questions? Okay, sounds good. And then I'm going to show you a little bit on the timing diagram because we all like that. Basically, the top is the system clock. It's the clock. Usually, it's the system clock, but it can be other clock. It depends on how you wired your circuit. And we have the chip select pin. Whenever you have and this chip select pin is one per peripheral. And you will put it down when indicating that it's the active one or the ones that should be responding. And it should be put down the entire time during the data exchange or data transmission. And then within that time, each of the bit got basically, you can think of them like swapped or like shifted between. And then this is the serial data out pin from the perspective of the master device. And this is also from the perspective of the master device. Basically, a bit of data in this case got pushed out and then shifted out, and then got, once all these operations done, the program will basically pull up the chip select pin again, and then indicating this whole transmission is finished. And the clock is just doing its own clock thing, usually for all the time. As opposed to later on, we will talk in the I2C, the clock is usually only operating while there is some active communication on the bus. In SPI, it's usually just keep going. And in this case, basically the data are locked in on each of the uprising edge, like rising edge of the S clock, and we actually have very large controls over this. We can control how or when the data got locked or being read, and we can control this by the clock phase and also the polarity. Basically, you can set it to be either at the rising edge of the clock or at the falling edge of the clock, as well as if it's when it's changed from low to high or change it from high to low. In total, we have like 4 different stages you can use. These are all, just depends on how you set up your SPI. These are all the configurations you can do based on how you set up the SPI. These 2 pins, each of them have like 1 bit. So 0, 1, 0, 1, and then in total you have like 4 different modes.
What's the difference between like the bottom left corner with the sampling edge and then the top right corner with the sampling edge? Because they're both like on the falling edge of a clock cycle.
Which one? Sorry. The bottom left of the sampling edge, the ones that goes down,
like
and
O1 and O2, because the sampling edge is on the falling edges.
I see. That's a good question. Let me see. What do you guys think? Oh yeah, I'm actually not sure. Let me check on that. That's a good question. Yeah. But I think usually what we normally do is use the pulling up as the moment to take in data. As I remember it, the main difference between these two modes usually happens when you have the like how is the first bit being set it up. If it's previously at a different stage and then you clocked it at the first ending edge of the falling down, versus here, say if you have the clock, if by default it's put on high, if it's not using the system clock, if by default you use on high, and then you use the falling edge of the first high to low as the starting bit or as the data, as opposed to on that one, if say the normal, during like no active communication, if it's not connected to the system clock, it's constant low, then that's basically different ways to trigger them. Yeah, I think I'll double check on this, but I think if you do connect it directly to the system clock, the difference is not that much. But if you connect it to a different clock, then that's where the difference is going to be. Hope that answers the question. Any other questions regarding these four modes? Okay, sounds good. Yeah, here is just a little bit more zoomed out view on how each of the different modes works. This is still using the similar clock, but just checking on them on four different modes, and we'll show you exactly when they're going to be checked at, like when the data is being latched into the system, basically. Yeah. I believe the two mode difference is usually used in when there's like no active communication happening on the bus, and the system clock was not connected to like a constant clock. That's the main difference. It happens for those two modes. And this is like a pretty typical SPI transaction. On the bottom here, we kind of have them shifted a little bit, but in reality, they usually happen at the same time. This is for like just show you how each clock cycle works and so that it looks, I guess, cleaner to a certain perspective. But usually the SDI and SDO, the two data shifts happens at the same time. And if we just look at this a little bit detail, this is clocking the data on the rising edge. So basically it results in an ASCII number of S, and then here ASCII number of F. And usually, although you have different controls, you can have different controls over how many bits of data you send every time. It's still quite commonly used for like a 8-bit system or 8 bytes per communication. The reason for that is, especially doing some of your final projects, is because the ASCII number is kind of a byte, if you are familiar with the numbers. So you can basically send in like a character, a char at a time. So to form some like meaningful communications, so to speak. Yeah.
How do the idle stages work? On the clock line.
Which one? The idle stage? Oh, you mean the S clock?
Yeah.
Yeah. So if say the clock is generated by the master, right? If it's directly connected to the system clock that always goes up and down, then it's always going to go up and down. But you can be basically controlled only by the master as well, because you can think of this. The clock that we did in the previous lectures, we have like hardware clocks. So if you somehow manage to directly connect that to this system clock pin between the masters and all the peripherals, then that's just going to always go up and down, right? But we also have the virtual timer. So if you created like a virtual timer and then connected that to the S clock between this SPI communication, which also happens quite often if you want to have like a very specific frequency or more controls over the frequency of the communication protocol used in SPI. Then you can essentially just enable the clock only when there's active communication happening on the bus. So yeah, just different ways of implementation, but both can work. And you can decide whether you want the idle of the S clock to be high or too low. Any other questions?
If it's connected to the system clock, are you continuously sending data that you can just ignore? Or
The data is only going to be read by any of the peripherals if the chip select ping was done. So if the chip select ping is on, there's just nothing on the bus, and no one is reading it. Yeah. Any other questions regarding this? That's a very good question. That is why in later I2C, when there's no chip select pings, the S clock, it became actually a quite important signal to look at to see whether there is active communication on the clock. Oh, sorry, on the bus. And yeah, so basically we have the SPI can usually be used for like pretty high-speed data transaction, and while it does not specify any of the maximum data rate inside of its protocol, it's not as well defined as other, say, UART or I2C communication protocols. But it's like a pull-up CMOS bus, and it's limited by the bus capacitance and the drive strength of the output circuit. If you remember from the previous lectures, basically, the pull-up of CMOS will be able to completely detach from the circuit and then reattach it when it's connected. And the bus capacitance can refers to, for example, it could be like the pings or like your wires between your wires and the ground plane, or even different wires. If you go to like super high frequency, there are like some crosstalks or noise between the parallel wires that goes to each other. And all just the physical wire itself. Say if you have like a very long cable, as we briefly explained in previous lectures, these things can also create laggings in terms of how fast the data can physically transfer. So while there are no maximum data rates being specified, there are like some physical limitations that we have to consider while using this communication protocol. But I think for the final projects you guys are working with, for most of the devices, the speed of the SPI should be pretty enough for your communication protocol. And you should use this as, I believe, probably the fastest ones you'll be used on your microcontroller, on this version at least. Yeah, some of these like standard speeds you can choose or use. It can be like from a couple hundred bytes all the way to 100 megabytes per second. So it's pretty fast, but depends on which type of data you want to use. If in the end the SPI speed cannot be keeping up with whatever you're doing, I think it's quite useful sometimes to think if you can do something on the data that's being transferring rather than still trying to increase the communication protocol. Because chances are they might have like too much redundant data or etc. that's being sent on the bus that you can be doing some like data filtering or like data pre-processing in order to limit the amount of data that needed to be transferred between the master device and the peripheral device. Any questions so far on the SPI? Okay, so let's do like a quick real-world example here. We have this gyroscope, and this is a pretty typical wire setup or like wire connections between the controller, microcontroller, and this peripherals. So we have our 4-wire connection, the SDO, SDI, the system clock, the chip select pin, as well as here we have 2 of the GPIO pins that are connected to the gyroscope chip. And why do we need that? Any thoughts? Anybody remembers from previous slides? So basically, we're using these as like the interrupt pins that if something, you should use as a flag, so to speak, to the microcontroller. That's something important, or there's like data ready here if you want to look at it. The master can just choose to ignore it, but it's something that can be delivered to the master. And remember, the master is the one that is the only one that can initiates the communication. The slave device or peripherals cannot directly talk to the microcontroller or directly talk to the master devices. And basically the data will be shifted between these two shift registers, and when that happens, the data got exchanged, so to speak, between these two devices. And some other ways, like we said, when we have, this is like an example of one of the other methods we do for getting the data back to the microcontroller, like the daisy chain method, when we have like multiple slave responses. So if you look, it might be a little bit too small, but basically, if you look here, all in this setup, all of the chip select pins are connected together. So then essentially it's one arrays of stuff that's controlled by this one master controller. And then each of the SDO of these peripherals are connected to the next SDI of that, the next peripherals. And it goes all the way back and then back to the main controller. So in this way, basically, each slave forwards data to the next, eventually reach the master. It's this type of setup is usually used in, for example, you have like sensor arrays or like LED controllers with a big chunk of LEDs. I'm not sure if you work with like the LED stripes that have like 50 of them connecting, and you can control them only use, say, like 4 pins because that's how they kind of connect it. And in this setup, it basically effectively eliminates the downside of using multiple chip select pins because they all share the same one, but it increased the latency of when the data or like when the data is going to be reaching the microcontroller. Okay, any questions in this one? I don't think you're going to be heavily tested on this, but just something good to know. Different methods of how the SPI can be set it up and communicate. And I think in practice, most of the times you can, that's how I do it mostly. You can almost treat them kind of like a big peripheral device rather than, say, you can treat like the whole LED array as like one device as opposed to like 50 devices that are connected together. So. Yeah, and a little bit graphics there from that point to that, and then it goes all the way. So on our STM32, basically we have 3 SPI modules, and each SPI module have a designated like the interrupt request pings. Can anyone think like why we have multiple SPI modules on our microcontroller? Any guesses? Talk to your neighbor, or anyone have the thought? Just raise your hand. Yeah.
Interacting with different peripherals at different rates, like ones that we don't want to have random crossing.
Yes, that's a very good point. So in case you want to have different, like for example, some peripherals are at say temperature sensors. You don't want to read temperature sensors, 2,000 times per second. It's probably not that useful. But some of the peripherals, for example, some for the analog input, like ADC channels, you want to, or those type of inputs you want to read as fast as possible because you want to have like a higher sampling or like a better sampling of that analog signal. So on those devices, you will use like a higher clock cycle for the SPI communication, and for the temperature sensor, for example, you will use like a lower speed clock. That is a very good point. Any other thoughts as well? Any other reasons? Okay. So that's a very big reason, the different speed. There's also different like data format. Remember previously we have the whole SPI give you much more freedoms on what type of data frame that you can send inside of the SPI bus, as opposed to previously in the UART. It's pretty set to be, 8 bits, between 8 bit and 10 bits. You have, depends on if you have the parity bits or not. But basically inside of the SPI, you have much more freedom. So by using different, by including various SPI protocols or SPI pings, you can have different speed, different data format, and just give you more controls that can work with like different types of peripherals. Depends on your need. Any other questions? Okay, yeah. So a little bit more fancier on the SPI we have on STM32. So two of these embedded pings that has what they call the DMA capability. Basically, what that is direct memory access. It's usually like a technique that's used for improved SPI communication by automating the data transfers, reducing like the CPU workload. Essentially, it's the basically like continuous data streaming at high speed that can directly access to the memory. Doesn't require additional like CPU intervention, etc. So another very cool thing we had is the hardware CRC, or the cycle redundance check. Basically, it's a better version of the parity check, like way better. Previously, we only checked like if basically 1 bit is correct or not. This is a you can think of each of the they have like hardware encoded number, and then each data byte or data bit that's got sent, you just divide it by that number, and then have like a remainder of, you have like a number of that, and then you check whether these two number matches from when you send out the data, and then when the master receive the data, and then check on that number. That gives you a much higher, or like it ensures that the data integrity much better than just like the 1 bit checkoff on whether it's an even or odd number of ones. So yeah. Any questions on these things here? I think a lot of them you're probably not going to be, well, you might in the lab, but I think in the end, in the final project, you might not need to worry too much about these, except if you're doing something quite fancy with super high speed data streaming. But yeah, so generally speaking, there are some pros and cons in any communication protocols. Of course, that includes the SPI. The pros here are the wiring is quite straightforward. It's only like 4 wires per peripherals, and you can really think of them, once you scale them up, it's like 3 plus n for multiple peripherals, plus the ground and power, of course, because the SDO and SDI pings are shared between these peripherals. And it's usually much faster than the asynchronized serial communication, for example, the UART. And it's also quite simple to implement, because you don't need to specify which address you're talking to or interacting with, as opposed to later on you will learn in I2C, that's how they identify which chip should be responding, or like which peripherals should be responding. Here they just use like chip select pings. The cons here, however, it doesn't scale as better as some of other communication protocols. For example, if you have, say, 100 devices that you're trying to be controlling, and if you chose not to use the daisy chain method to control them all as one batch, then essentially you need like 1 chip select pings per device. That's going to be a lot of burden on your system design, as well as like wiring or quite complicated circuit design. And there's no like acknowledgement abilities, and essentially is that it wouldn't know if the transaction is finished, as opposed to, again, later on in I2C, we have like a 1 bit dedicated to the acknowledgement, or not acknowledgement, meaning it's failed to read your data. In SPI, it's only just master kind of dominates everything. If one of the slaves silently failed, you wouldn't know until some amount of data is being transferred back through either interrupt channels or through some other daisy-chained data buses. And yeah, the controller is the one that initiates all the communication, and the peripherals must wait within this SPI communication protocol. Any other questions regarding SPI in general? We're going to move into I2C next. So, okay, here we go. Next, we're going to talk about the I2C, the Intel integrated circuits. There are different pronunciations to this. You can call this I2C or I2C. I just call it I2C because it's a little bit shorter and easier to pronounce. And as usual, we have different types of additional documentations that you can read to enhance your understanding of this communication protocol. Additional ones, we have a user manuals from the NXP that's specifically on the I2C. The other two are like pretty general on, well, the other two includes both I2C, SPI, and the UART communication. So what is I2C? Yeah, Intel integrated circuits, you can pronounce it in two ways, and it's originally invented in the very early days before any of us were born, for sure, I think, by Philips for like television sets. And today it's like pretty much like the de facto standards for two-wire communications. It's being used for a lot of devices and peripherals that are inside of the embedded system today. And in fact, I think, yeah, all these companies basically have these peripheral devices intended for, equipment with the I2C communication. And in fact, a lot of the devices you see nowadays, like once you starting to purchase or selecting the sensor modules for your final project, you'll learn that a lot of devices have both like I2C and SPI communications embedded together. So that it's just much easier for the manufacturers to equip both of them in the chip so that they don't have to make like two versions out of it. Yeah, and another cool thing is, since 2006, there is no licensing fee on implementing or using I2C on your device. What you have to pay, however, is an address that's being allocated by the NXP that will basically be acting like the chip select pin in the SPI. And let me show you how that was done in a few slides. But next, let's first look at the typical like wired up version of the I2C system. Okay, so yeah, basically we have essentially two wires that's being shared by a bunch of peripherals. No matter how many ones you have, actually that's being shared by the controller devices as well. So it's like a multi-master, multi-slave system that's using, everything is relying on this two line. And it works quite well. All of these lines are the open drain, and then you need like additional pull-up resistors for that. That's being usually connected to the ECC, and each of the device have a unique address. Usually, most of the time, we'll talk about one of the cases they don't have, but usually they will have their unique addresses, either 7 or 8 or 16 bits, and those addresses are purchased from NXP based on each of their device. And we also, the speed of this communication, quite interestingly, is kind of depends on what's the value of the pull-out resistors you used on the circuit. And these are just some like references you can use. At low speed modes, typically people use 4.7K, and standard mode you can use like 3K, and the faster mode you can use like 1K. You can think of this like a trade-off between power consumption versus speed. The lower the resistor value is, the more currents will be drawn from the system, and hence more power will be basically used during this communication. But you get to transfer faster. So some trade-offs in building this I2C. I think most of the time 4.7K should be pretty good for most of the use cases. Yeah.
What's the reason for the resistance speed relationship?
What is the reason for the relationship? Because, so basically it depends on the load you put, affects the speed on how fast the signal can be pulled up and down, essentially. Yeah. Any other questions? Okay, sounds good. So yeah, we have the open drain bus. Both of the lines are open drain, and then you have to, like we said, we have to have the additional pull-up resistors to be able to have the have these two lines not being floating. And there's a few reasons for that. First is the preventing like bus contention. So if, say, multiple devices trying to drive the bus high and low simultaneously, if we don't have if we just keep the circuit like pull-up resistors, for example, inside of the system, that could cause sometimes unintentionally short circuits between the system. So the two pins, SDA and SCL, are basically always open drain. Another quite common reason is that with this setup, you are actually able to drive the peripherals that runs on different voltage. For example, if you have your microcontrollers run on 3.3, and as long as you chose like a matching resistors on your peripheral side, you will like matching the voltage level of high and lows between these two based on the resistor value you choose, and then you're able to have a 3.3 system that interact with, say, like a peripherals that does 5 volt, that runs on 5 volt. So that is quite convenient, and I think these two are like the main reasons. Another reason is it supports like multi-master communication through like thing called like wired AND logic, which we'll talk in like next slide. But basically prevents the bus shortage or bus contention. And the second is supports like multiple voltage usage. This is the main reason why we're using the open drain for this. And again, this is like a quick figure showing here how like wiring is working. It's very straightforward, just two lines from the controllers. SDA goes to SDA, SCL goes to SCL, and those lines are shared by all the peripherals, and they will be connected via a pull-up resistor to the VCC, so that if there's nothing happening, it will basically stay at high. Yeah. Any questions so far? We're good? Okay. And we don't have to do this. Okay. And again, we have the timing diagram here. Basically, how a data transaction happens. To start with, we have what they call like the start condition. Basically, it will wait to see if there is any traffic on the bus for a little while, and then going to put like the data line SDA down. And how does it see if there is no traffic on the bus? It will usually by looking at SCL. So if the SCL just stays high for that period of time, that means there's nothing happening on the bus right now. If you have like lows during that period of time, that basically indicating something is happening on the bus, and this current communication has to wait until this existing communication is already finished. And but anyway, if it detects it's constantly high at that moment, and then there's basically cleared on the bus, and then what they would do is it will pull down the SDA top there. So let's see here, and that would be indicating the like a starting bit basically. And while we still clocking the data on the rising edge of this clock, in the I2C communication, the data line, the SDA line, has to stay constant during the entire high of the SDL. And the reason for that is we are kind of using the changes of the SDA. Here we use it for like the starting bit, right? At the end, we use like this one rising edge while the SCL is high as the ending bit. or like the stopping bit. So if we have some data changing during the clock cycle, while it's maintained high, it will misread it as a stop signal, oftentimes, or start signal. So that will mess up the system. So what's happening is, if you look close here, imagine this is like 1 bit of the data, right? And during the entire cycle of the SCLs being high, this data bit has to stay constant, although the data is already locked at the rising edge. And all the changes on the data line has to, if it needs to be changed, has to happen while the SCL is at the low stage. Does this make sense to everyone? It's a little bit complicated, but because they share the same SCL lines and the SCL signal is purely generated by the master or whoever was sending the data. So that usually works out. Any questions on this? Okay, perfect. So yeah, it works. So what happens if we have, say, like one way trying to enter the starting stage? What happens if we have, say, two masters trying to talk to some slave at the same time, right? And what if they reach the bus altogether? How do we do about that? Previously, if someone arrives late, it would be just checking the CL signal and then just back up and until the next round. But in this case, so they have what they call like a wired AND bus. Essentially, it's kind of like a low stage or 0 stage dominant situation. So the two masters will basically sending out the data at the same time. And whoever sends, how do I put this? Whoever keeps sending 0 or whoever sends 1 first get kicked out. So whenever, every time when they send out the bit, they will always check what's the current stats on the bus at the moment. And if both of them send 0 and on the bus is currently also 0 or low, they keep sending the next bit. And then when some of them, say the master 2 sends out a data 1 to the bus, and then the master 1 sends out a data 0 to the bus, and then the master 2 will notice that the data currently on the bus is different from whatever data he is sending. So that one knows it's his turn to back off and then wait until this current communication is finished. So basically, when this transaction request happens at the same time on the bus, they will be, it just depends on who sends more zeros, I guess, or who sends more zeros at the beginning. And the zeros dominate. Okay, does that make sense? It's a little bit complicated and not very intuitive, but that's how they made it, and it works quite well. So, yeah. Any questions on this? On how they clearing the, basically determine what's the arbitration when there's like multiple controllers or multiple masters trying to communicate. Okay. So this is like a frames of data looks like. Basically, let me just put it all out at once. Yeah, so basically, as we said, it's going to be sending out the address first. The address here will be determining which peripheral is trying to talk to. And at the end, it will be like an acknowledgement bit standing out. And if the peripherals, well, that acknowledgement bit, in this case, it's being sent from the slave device or the peripherals. Basically, okay, we send out, the master sends out the targeting address first from, for example, this one is a 7-bit address. And then the 1 bit after that is the write or read, indicating whether it's trying to read from that peripherals or write to that peripherals. And then after that's gone, and then the peripherals ideally should get the data and then basically sending back a acknowledgement bit to indicating whether it's received this command. It could send like nunc. This is like an acknowledgement bit. Nunc is basically non-acknowledgement. So, I didn't get it or something. But let's say this time just successfully send. And then after that, the next will be the actual data. In this case, it's an 8-bit data. And then again, at the end, it's the acknowledgement bit sent from the peripherals or the slave devices, indicating whether it received the data, or if it's trying to write to it, or receive the command of reading, etc. Yeah, and you will notice that the S clock is only active while there's active transactions during this period. If there's any other masters trying to initiate any communications, it would first check the SEL, and it will see something is happening there, and it will just back off until it's turn. And this is what the actual real data could look like. For example, the first we have the starting phase. Essentially, let's see if we can see this clear. Basically, the clock is high all the time, and then it enters the start phase. It's still kept high to just checking if there's anything on the bus right now. And SCL is clear; it's always high, so it's good. And then check on the SDA. Nothing is happening. Basically, start to pull the SDA down. That indicating the starting bit or the starting phase of this I2C communication. You will notice that this edge here, when the S clock goes down, is after this SDA goes down. That's because this change of the SDA happened during the SCL is on the high stage. And during each of these communication, during each of the data transactions, the data bit has to be high for the entire times while the SCL signal is high. That's why you will see these are a little bit wider than the little peak down here on the SCL. And the first is the address, and then write signal, acknowledgement, got, and then later on to the data that's actually being right into that peripherals. Any questions on this side? This is basically what a real data plotting would look like if you have, say, a oscilloscope. What's tricky here is compared to, for example, the SPI, because they use two different wires for the communications between the masters and the peripherals. It's quite easy to know what's being exchanged between them and which direction that is, right? However, instead of the I2C, because it's all using the same wire, you have to always, if you decide to use the oscilloscope for debugging, you should always notice or pay attention to see whether the data that's being sent through the bus is from the masters to the peripherals or from the peripheral devices back to the controller or masters. Just make sure you kept some additional notes on that. Yeah, so basically, we talked a little bit about the acknowledgement bit, or the not acknowledgement bit, hence the ACK or NAC. Basically, the SDA lines remains high during these clock periods, and then that would be interpreted as a NAC. That could happen in a few different ways. For example, if the receiver or the slave device is unable to receive this data and nothing happens, so that line was just left there unchanged. That's a NAC, so nothing was received. Or if the command that later on the master writes into the slave device was not recognized by the slave device. For example, it's trying to set a mode of this peripheral slave device to a special mode, but that device doesn't have this mode. Say if you're setting, I don't know, whatever you're trying to send to IMU sensor to a temperature sensor. And the temperature sensor have no idea what you're trying to do, right? So it will basically raise that NAC flag. So I don't know what happened. And these are the cases usually when the ACK or NAC signal is being sent through by the slave device or peripheral devices. there are also cases when the controllers can send this signal. That's when the controller is in like the receive mode or like the read mode. And then when it's done reading the data, and you will be sending essentially, in this case, a NAC signal to indicate it's finished this process. And it will send a ACK signal every time when it received a byte. So receive a byte, ACK acknowledgement, receive the byte, acknowledgement, so the data will keep coming in until the master or controller sends a non-acknowledgement that indicates the end of this receiving or reading phase. Does that make sense to you guys? This acknowledgement, non-acknowledgement bit? Basically, you can think of it like a flag that between this multi-master, multi-slave communication protocol that you have an additional flag or bit that's used to indicating whether indicating first whether the data is successfully sent, and as well as if this data makes sense, or it should be keep doing what it's been doing until it's done. That would be the controllers in the receiving mode. Okay, I see a few nodding heads, so I assume everyone gets it. Yeah, so this again is the like a real world signal, and you will notice that at the end of that, that's like a non-act bit there. That's because if you look here, it's the controller is in like the read mode, and then that's like after it's finished reading all the data it needs, you have like a nunc signal put into the bus. This is from the controllers. This signal can come from either masters or from the slave peripherals. So just depends on which mode it's currently in. Usually in the address periods, the acknowledgement or non-acknowledgement, it's almost always come from the slave peripherals. Yeah.
What if the controller fails to receive data?
What if the controller fails to receive the data? So it will if the data was in multiple byte, they were basically not sending that acknowledgement bit, and if the whole system was stalled there for a little bit, there would be like a additional system that pulls or forces the communications or forces the SCL lines to go up high. So you can kind of run into like a timeout, and then everything got set back. If the receiver is not, it's got stalled there for a while. There's also other times when I think was that in SPI or? Yeah, so basically that's what could happen. Any other questions? Okay, cool. So how does the peripherals, write data? This is just another more in-depth, diagram of whatever that real diagram is. Essentially, at the very beginning, it's at the start condition. As the SCL was currently at the high because there's nothing happening, and for a while there's still nothing happening. So assume it's available, and then it pulls down the SDA line, indicating that's the starting of a communication. And then the CL basically being, clock that's being generated by the masters to doing a bunch of the clock cycles, and then the first the address will be like address data that's being sent through the SDA line, and then a bit of read or write, and then a bit of the acknowledgement sent by the slave or by the peripheral devices, and then after that's all set up, it will be doing the data transaction. In this case, 7-bit and then or 8-bit, and then it's the additional acknowledgement bits coming from the slave if it's a write, which in this case it is. Yeah.
Is the peripheral choosing where it's writing stuff to?
Is the peripherals choosing It's the master that chooses where to write. It's basically determined by the address here. That's where the data is going to be writing to. Yeah, it's usually from. Yeah, if it's writing from, or if it's receiving from the perspective of the master device, it will be read, and then the data later on here, the data will be sent from the slave peripherals back to the master or controller, although using the same wire SDA.
What kind of address, is it an address space that's contained on the peripheral, or is it an address space on the chip?
It's the address that's being assigned by the I2C communication. Remember, like these companies have to buy a specific address from the NXP company. Those are the assigned address that's hard-coded onto each of the chip. Yeah.
So what do you do, like our address conflicts, I think, where like two devices will have the same address, and how do you handle that?
That is a very good question. So how do we handle that? Well, there are different ways to handle that. The most straightforward way is to use two different I2Cs, so that each I2C only have one address for that. Or you can implement it a little bit more complicated. You can put some additional mux to the system, for example, or something like that. Basically, adding some additional select pins to the system. If you only have, say, one I2C channel or limited I2C channels to interacting with devices with the same addressing, essentially. Or you can group them together. If it's the same device, and then you can say if they're all LEDs, right? If you can control them in like a more, different ways that can somehow use the same address, but just the data got shifted between them. That's also something you can do. Any other questions? Okay, cool. Yeah, so basically, the clock is always going to be generated by the controllers as the same as in the SPI. Here it's basically only high or only active when there's something happening. Well, I guess it's the same for SPI if you configure it that way. But in this, it's almost always high when there's nothing happening. In SPI, you could choose however you implement that clock. That's because the SPI have an additional chip select pin. In this one, it doesn't. And also because the I2C have multiple masters to talk to multiple peripheral devices. So it's like essentially a more complicated setup using as well as using less amount of wires. So that's why how you use these wires is always also going to be a little bit more complicated. Yeah, and you have always make sure that during that CL is high, the data bit does not change during that entire high period. Only changes during when the CL signal goes too low. And on your device, on your like the STM32, we actually have 4 I2C modules on it, and the reason for that, I think, as one of you guys mentioned, is mostly used for if we have, say, multiple devices of the same address. Then these things can be quite convenient to use. And another thing, I think the CL signals, usually there are different ways to implement this. Usually all these master devices or all these slave peripherals, they use the same frequency of the SCL. You could implement it different frequencies on this clock. It's not that common, because you have to make sure all these slave peripherals are able to operate on the highest speed of the clock that you have on the bus. Otherwise, it will cause some like unintentional behaviors. So if that was the case, why not just use the higher speed ones? So it's usually used only if you have, say, like 1 or 2 modules that requires, you want to like minimize the power consumption, for example. Those are the times these will be used. But usually it's implemented as the same clock signal when it's active. But you could implement different ones. Yeah, and we have some hardware tracking on these on these I2C channels, as well as the acknowledgement pin controls, and we have the 4 interrupt signals that connects to each of these I2C peripherals as just like, other communication protocols or other GPL pins. And again, so everything has pros and cons. The pros of the I2C is that it's very easily to wire, and it's only like 2 wires across, a lot of master controllers and slave peripherals altogether, and just additional ground pins or VCC pins if needed. And it's widely supported in the industry. The cons here is the whole open bus setup makes the debugging a bit harder, because everything is just using like the same bus line for the data transaction, and you kind of have to know which direction it's going to and which device is it going to or going from. And the maximum speed is determined by the additional hardware, as well as the arbitration. It works, but if you say want to hardwire or like hard set any of the highest highest priority that can interrupt with any other ongoing transmission, that's going to be very hard to do with the I2C communication. So, yeah. Any questions on I2C at this moment? Okay, perfect. So yeah, just a quick review on all the overall serial communications as well as the different communication protocols we talked about. First is the UART, basically have like 2 wires, TX-RX connects to the RX-TX of the device. It's kind of like a point-to-point or device-to-device communication. It's asynchronized. It's relying on additional signals or additional handshaking signals or flags to determine what's the how should the receiving side interpret the data. And then we also have the SPI. Basically, the wiring is pretty straightforward, 4 wires, and then there are only 1 master controllers that controls all bunch of the slave peripherals. And the package size can be more flexible, like the amount of the data frame, basically. And on the I2C, which is we just talked about, we have the whole bus is kind of like open for everyone. All multiple masters and multiple slave peripherals can be sharing and will be sharing this two-wire system. And then each device is basically have like a unique address. That's how they determine where this data should be going to or going from. And it has the speed and external pull-up needed for connecting the circuits, basically. And in the standard, like these are basically some of the quite common communication or common setup, like 4.7K is pretty widely used. I think a lot of your sensor modules will use that for the, yeah.
Could you explain the wired and concept?
The what, which one?
Wired and concept?
Oh, yeah, the wired and is basically when there's 2 masters are trying to write to the bus at the same time, whoever writes 0 and the other one writes 1, that 0 get to take over the bus. And that whoever that writes the 1 get kicked out from the communication. So essentially every time it sends out the bit, it will check on the bus to see if that matches whatever the bits it's trying to send on its own. Any other questions? Okay, perfect. So this is just like quick summaries, asynchronized versus like non-synchronized, and some arbitration ways. We have like select wires, or like the wired and methodology. We also have the topology. Basically, the UART is like 1-to-1. The SPI is 1 to a lot, 1 to n, and the I2C is like n to n or 1 to n, depends on how you connect them. But it's able to support n to n. The speed wide, the SPI is the fastest, and the I2C is kind of in the middle, and the UART is the slowest. Cool. Any questions? If you don't have any questions, this is the end of today's lecture. If you have additional questions, please feel free to come down to me and we will discuss. Thank you. Yes.
So I got confused there at the end. So for I2C, right?
Yeah.
The wire